Alright, so we're going to start characteristics of rational functions, and I really like this. I think it's kind of fun, but you'll be able to see how everything that we've been doing with simplifying rational expressions comes together to tell us stuff about rational functions. So these are also very important when you get to calculus. So there are four main things to find when you have a rational function. First of all, a rational function. If you think about the root word of a rational function, what everything we've been doing this entire unit, is a ratio. So this just means this is a fraction that is a function. So I've got a fraction. So four main things to find are wholes, vertical asymptotes, horizontal asymptotes, and slant asymptotes. You may have looked at these few things before, but maybe not slant asymptotes in Algebra 2 or Integrated 2 or whatever you've taken. So we're just going to review these three and then go over how to find this. And this will also have to do with our long and synthetic division, so you'll see why we did all that stuff. So wholes are the first thing. And so these are factors that cancel out. So when you do your factoring and then you have a factor that cancels, that's what gives you a hole in a graph. And so these are called, when you get to calculus, removable discontinuities, because when you cancel them, instead of creating an asymptote like it would normally, since they cancel, that factor cancels, there's going to be a hole in the graph at that point. So let's look at how to find a hole. So I'm going to factor the top. I'm just going to go about this like I'm simplifying a rational expression. So this will be x plus 1, x minus 1 over x minus 1. And you can see that here the x minus 1s are going to cancel out. And so that factor at x minus 1, wherever that factor equals 0, there's going to be a hole in the graph. And so x minus 1 equals 0 would be at x equals 1. So there's a hole in the graph at x equals 1. Well, if I'm looking at the graph, a hole is just going to be represented by an open circle. And so if there's a hole in the graph at x equals 1, that doesn't mean that there's a hole right there on the x-axis at 1. It could be up here at 1, or it could be down here at 1. It's going to be somewhere, and we need to find where that is. So the way that you're going to go find where the hole is exactly is by taking this value and plugging it into what's left over. So you need to find a coordinate for the hole in the graph. So your x coordinate is just your 1, and your y coordinate comes from, you find by plugging the x coordinate into what's left over. Okay, so I'm going to plug this into what's left over. What's left over is going to be that x plus 1. And so if I plug in 1, I would have 1 plus 1, which is just going to give me 2 for the coordinate. So if I were to go graph the hole in the graph, here's my open circle. I would go over 1, up about 2, so there would be a hole in the graph right there at 1, 2. So that is how we find holes. Let's find a hole for this one. Now, this right here, we cannot factor just normally. So we're going to have to use that process that we did whenever we had to factor using synthetic division. So I'm going to go plug that into my calculator and find a 0 that I can use to break that down and use synthetic division. While this calculator's opening, let's go ahead and factor the bottom of this. So I'm going to factor the bottom. I know how to factor that. That's just going to be x and x, 3 and 1. This will be a plus 3 minus 1. So now that the calculator is open, I can plug this in and use synthetic division to factor it and see what's going to cancel, to see where there are holes. So I'm going to plug in x cubed plus 4x squared. So into my y, clear that out, x cubed plus 4x squared, and then plus x minus 6. So when I plug that in and go to the table, I can see that there are a couple of different zeros that I can use. So I'm going to use 1 to do synthetic division. So 1, then 1, 4, 1, negative 6. And so if I bring that 1 down, 1 times 1 is 1, that'll be 5. 1 times 5 is 5, this is 6, 1 times 6 is 6, so there's a 0. So from this, I get a 0. And so as a factor, that's going to be x minus 1. And then this just represents x squared plus 5x plus 6. And so then I can factor this, and I'll end up with x and x, 2 and 3, plus, plus. So I'll end up with x plus 2 and x plus 3 that are also factors. So that's how I'm going to factor the top of that. Now we can see that x plus 3 is going to cancel and x minus 1 is going to cancel. So there are going to be two holes. So the holes in the graph are going to be where those factors equal 0. So one is at negative 3 and one is at positive 1. And so I'm going to find their y coordinates by plugging negative 3 and 1 back into what's left over. So what's left over is just x plus 2. So negative 3 plus 2 would be a negative 1. And then 1 plus 2 would be a positive 3. So the two holes in the graph are there. And if we were to graph this entire thing, you could check that there are actually holes in the graph. I'm going to show you how. So let's go back and put parentheses around this so we can put it all over our denominator. So that's x squared plus 2x minus 3. X squared plus 2x minus 3. And so when I graph this, I can see what the graph looks like. It's just going to look like a linear graph. Okay, and that should make sense because these two factors canceled out and I was just left with x plus 2 and this is linear. So I'm going to check to see that there are holes. Your calculator, the pixels are really small, and so you can't really see holes on your calculator, but you can check to see that they're there. So I'm going to hit trace, negative 3, and it's not going to give me, it's going to give me like no value for my y. And if we go to the table at negative 3, there's an error. And so there's also an error at 1, and that's from this hole. And that's because those two values, negative 3 and 1, would make the bottom of this fraction 0. So the calculator doesn't calculate this y value. It just tells me that there's an error there because there's a hole in the graph at these two places. We find this so we can actually go physically graph the graph, and we know where the holes are in the graph. So those are the holes in that one. Alright, the second thing that we need to find are vertical asymptotes. So let's just talk about what an asymptote is. A vertical or slant line of a graph which the function approaches but never touches. It's not actually part of the graph, but it's an invisible line represented by dotted lines. So we're not going to draw these as solid lines on our graphs, but we're just going to represent them by dotted lines. And so these are called non-removable discontinuities because we can't just remove them, okay, by canceling those factors out. So any kind of asymptote is a non-removable discontinuity, or a vertical asymptote is a non-removable discontinuity. So let's find the holes and the vertical asymptotes of this function. So first thing I'm going to do is factor an x out of the bottom. That'll leave me with x squared minus 4. And then I'll have x plus 2, x minus 2. And so then the factor that cancels is x. So that means there's a hole in the graph at wherever x is equal to 0, and that's just 0. And so then this is going to leave me with 1 over x plus 2, x minus 2. Alright, so the y-coordinate of the hole, I would just plug in 0 for these x's. So that's going to leave me with 1 over 0 plus 2 is 2. 0 minus 2 is negative 2. So that would be negative 1/4 if I simplified. So negative 1/4 for the y-coordinate. Now the vertical asymptotes are going to be zeros in the bottom that do not cancel out. So these are the two factors that did not cancel out, and so these are going to give me vertical asymptotes. So I'm going to have a vertical asymptote at x equals 2 and negative 2. And I just got those by setting these two factors equal to 0. So this one gives me negative 2 and this one gives me positive 2. And let's look at the graph so you can see what the vertical asymptotes are going to look like. So my function is x divided by, I'm going to put parentheses around the bottom to keep it together, x cubed minus 4x. Minus 4x. Alright, so when I graph it, here's our graph. And so you can see that where the function breaks apart and kind of goes different directions is where your vertical asymptotes are. And so you can kind of see that that's at negative 2 and positive 2. Now, the way that you can check to make sure the hole is actually there is by hitting trace 0. So we can go to trace 0 and it doesn't give me a y. Or we can go to the table and I should have 3 errors. I have one at negative 2, 0, and positive 2. And so you can check all of your discontinuities that way. Alright, let's do another one. So I can factor the top. This is going to be x and x, 2 and 1. And then I'll have plus plus. Now I factored that to see if anything would cancel. Since nothing does, I have no holes in the graph, so there are no holes. But I do have a vertical asymptote from what's left in the bottom. So the vertical asymptote is going to be at x equals 1. And when you write these, you need to make sure that you have x equals a number. These are x equals a number. If you don't, then this is not an equation for a vertical asymptote. And remember, a vertical line has an equation of x equals. So it's really important that you write x equals. If you don't, I'm going to count off. Alright, we'll save horizontal asymptotes for the next video.